And welcome back. We're going to be working on example 3 from the chapter 3-5 notes. So let's take a look at example 3 here. Okay, this is very similar to a problem example 2. The only difference is that we are going to be working vertically instead of horizontally. So let's take a look here. An elevator accelerates downward, so we're accelerating downward, okay, from a speed of 1 meters per second to 6 meters per second in 5 seconds. Okay, so that's situation 1. So let's write down our givens for situation 1 here. One thing to note is that since it's moving downward, we have a negative velocity. So the initial speed, so the initial velocity, okay, ends up being a negative 1 meters per second. And its final velocity is 6 meters per second, and negative 6, don't forget that, meters per second, and with a time of 5 seconds. So what we're supposed to do is we're supposed to calculate the acceleration for each situation. So we'll say acceleration 1 is question mark. Okay, so calculate the acceleration for each and explain why both a values are negative. So again, the a values should both be negative. So let's draw a motion map for each of the elevator's velocities for each situation, including arrows for. So for a motion map, we include vectors for velocity and a vector for acceleration at each moment in time. And let me change my color of my pen here. So let's get started here. At 0 seconds. Okay, so here we are. The velocity of the elevator is negative 1 meter every second. Okay, this is at time 0. It's 0 seconds. 0 seconds. Okay. Let me just change colors here. I'll draw the accelerations vectors right here. Okay. And the acceleration vector here is, well, we got to figure out what the acceleration is first. So let's figure out what the acceleration is first, and then we'll be able to draw the acceleration vectors. Okay. So the equation for acceleration is change in velocity over time. Okay. We know change in velocity is final velocity minus initial velocity over time. So here's our equation with variables. We have our givens. Let's plug our numbers in and calculate our we'll call this acceleration 1. So acceleration 1 is our final velocity is negative 6 minus our initial velocity is negative 1 over the total time of 5 seconds. So acceleration, okay, so you have a negative 6 minus a negative 1. This is the same as adding the opposite. So negative 6 plus 1 is negative 5 over 5 then, which is negative 1.00 meters per second squared. So what does this mean? So here's our acceleration 1. What does this mean? This means for every second of time that goes by, the velocity is going to decrease by 1. So since it's 1 right now, at 1 second, so let's draw, here's our position at 1 second, 1 second. The velocity is going to increase by negative 1, or decrease by 1. So it's negative 1 right now, so now its velocity is going to be negative 2. So the vector needs to be about twice as long as this initial vector. Okay, velocity equals, so negative 1 minus 1 is negative 2 meters a second. Acceleration, okay, here's my acceleration. These are my a values here. Okay, this is going to be constant. The acceleration is constant all the way down. So my a values are going to be negative 1 meters per second squared. I'm running out of room, so I didn't include the unit here. But the acceleration is always going to be the same. So the acceleration is going to be negative 1 all the way down. See how that works? Another way to think of it is if you have your velocity, add your acceleration, that'll give you the velocity at the next second. Negative 1, this is minus 1. Negative 1 minus 1 will give you a velocity of minus 2. Okay, so the next one next position right here, here's the position. That dot represents the position of the object, of the elevator. You'll have a larger velocity yet. Velocity equals -3 now, meters every second. Acceleration is still constant at -1. Okay, and we have to go for 6 seconds. Right, 6 seconds, we're at 3, 4, that should be longer yet. Might run out of room here. 4, 5, looks like I am going to run out of room, but you get the point. So that'd be 5. Sorry, I didn't include the times. 2 seconds, 3 seconds, right here, that's 3 seconds. This is 4 seconds. Okay, at 4 seconds, our velocity is -5. Our acceleration is still -1. Same here. These are all the same. -1. Okay, and then at 5 seconds, you have another one. I'm going off the screen, but you need to make this arrow longer than the previous arrow, and that will be velocity is a -6 meters every second. Okay, so this is the motion map for the first problem. I know these motion maps can get a little complicated and a little messy. Just try to line them up as best as possible. I have to still include my acceleration right here because it's still accelerating. So my a equals -1 here. But this arrow right here extends downward longer than this arrow right here because if you look at it, its speed's increasing every second in time. Okay, now let's look at our second situation here. So now the elevator is moving up. Okay, the elevator is moving up, and it looks like it is slowing down to a stop. Okay, let me just get a darker pen here so you can see this better. So it's moving up and slowing down. Okay, I might run out of room here, so I'm going to try to move this over if I can. 1 second here. Alright, so what I'm going to do is I'm going to, my other problem is still there. You can see it's right there. I'm just going to increase it or make it transparent so I'll be able to write. So here's the problem we just did. You can pause it right now if you need to look at it. I'm going to get rid of it here, and let's work on the next section of it. Okay, so first of all, let's find the acceleration because we know the velocities. Later it is moving up and slowing from a speed. So the initial velocity is it's moving up, so it's a positive. I'll just put that there. Positive 4 meters every second. It's stopping, so its final velocity is obviously going to be 0. The time it takes for it to decelerate is 1.60 seconds. When you calculate the acceleration for this, and then we need to figure out create a motion map here. So let's go ahead and do this. Let's just find the acceleration quick. The acceleration is change in velocity over time. We can call this acceleration 2. Remember, change in velocity is final minus initial velocity divided by time. Let's plug in our numbers. This is the equation with variables. Let's plug in our numbers here. Final velocity is 0. Initial velocity is 4 divided by 1.6. And that will give an acceleration of -2.50 meters per second squared. So what does that mean? That tells us that the speed is decreasing, or it's increasing downward by 2.5 meters per second for every second in time. Okay? So since it's moving up, since its velocity is initially positive, it will be slowing down. Remember, when the velocity vector and the acceleration vector are pointing in opposite directions, the object is slowing down. So let's take a look here. I'm going to try to make this so I can fit it on this page. Usually I draw these way too big. Time 0, we're right here. Okay? 0 seconds. The object is moving at a positive 4 meters every second. V equals 4 meters every second. Okay? I'll draw my accelerations over here just to note these are my acceleration vectors. My acceleration is always going to be -2.5. Let me point that down over my A here. Okay, Okay, acceleration is a negative 2.5, and this is going to stay constant the entire time. This is at 0 seconds. At 1 second, I'll be right here. That's the location of my object. 1 second. My velocity now, so remember how to do this. Take 4, add the acceleration, so 4 minus 2.5. Okay, let me backtrack a little bit here. This problem is a little bit different because, oops, where's my eraser at? Because we are not getting the same, you can't split this up based on seconds. So this motion map is a little bit different. Don't worry about it. I won't give you a problem like this on a quiz, but this is still good practice when we're moving up and accelerating downward. We're gonna show the position, velocity, and acceleration at every 0.4 seconds because this will give us some nice numbers here. Okay, so this position represents time at 0.4 seconds, so 0.4 seconds here. Okay, our acceleration is still constant, going down. I'll put a little line here to note that they're the same. Okay, a equals negative 2.5 meters per second squared. Okay, so I did the math, and so every second, so every 0.4 seconds, my velocity is going to decrease by 1 meter every second. So if I'm at 4 here, ends up being at 0.4 seconds. My velocity is 3 now meters every second. Okay. Next one, 0.4 plus 0.4 is 0.8, so at 0.8 seconds, my acceleration is still negative 2.5 meters per second squared. This ends up being 2 meters every second now, so we're decreasing speed. The elevator is slowing down. It's going to be slowing to a stop. Okay, at 1.2 seconds. Okay, our velocity is going to be 1 meter every second. My acceleration is still constant. Okay, I did this a couple times. I'm showing that they're all the same. It's redundant to keep writing this down. 1 meter every second, very short vector here. And then at 1.6 seconds, which it says right here, 1.6 seconds is at a stop. 1.6 seconds. Velocity is 0 meters every second. It's not moving yet. We can still say it's accelerating. Okay, it's the same. Okay, so you can see the elevators as a high speed and slowing down. You know, in between these times, it's still slowing down, but we're just noting it at, it's like we're taking snapshots at every 0.4 seconds. 0.4 seconds, 0.8 seconds, 1.2 seconds, 1.6 seconds. You can see how it's slowing down to a stop. Acceleration stays constant. So you need to realize that when the velocity vector, which in this case is pointing up, is opposite of the acceleration vector, is pointing down. Okay, that means it is slowing down. Okay, slowing down when we have a velocity vector going up, an acceleration vector going down. Or you can go left and right. You also have velocity vector going down, acceleration vector going up. Whenever they're opposite directions, no matter if it's going left to right, up, down, whatever, okay, that means the object is slowing down. So in this case, the first situation, let me get that back up here. Oops. The first situation might be hard to see here. Okay. In the first situation here, let me get rid of the new one. It's speeding up. We have the velocity going down, the acceleration going down. That means it's speeding up. Okay, so it's accelerating downward. Okay, and then the second situation, the acceleration, it's still accelerating downward, but it's moving upward. That means it's slowing down. Okay, so the accelerations are still pointing down, but because it's moving opposite, it's moving up initially. Okay, it's going to slow down. If this was like a tennis ball that you threw up in the air, Okay, this would reach an apex, stop, and then start to accelerate.